Welcome to the HVAC-Engineering-Techie channel. This is a channel where we talk about all things HVAC. We talk about engineering design, construction, equipment, systems, test and balance extensively, controls, and efficiency and performance of systems. So these videos are basically an educational device to help you advance your career. So today we're going to be talking about water flow and pressure calculations. This is engineering calculations. So this is something that all technicians need, especially tab technicians. So we're going to talk about that. But before we do, I'd like to ask a big favor. Would you mind becoming a subscriber to the channel by clicking the subscribe button below and hit the like button? That costs you nothing. It's absolutely free. I will never bug you. What it's for is that Google uses that information to evaluate this video on their platform. So if you do that, I'd really appreciate it. So let's get started talking about water flow and pressure calculations. Okay, so let's start talking about water and the calculations for water. The first thing we want to talk about is head calculations. What is water head? And that's converting PSI to foot of head. It's just a little simple formula. And it's the head equals P times 2.31 divided by the specific gravity of the fluid. So if the specific gravity is 1, which is clean water, then H equals P times 2.31. So basically there's 2.31 foot of head for every PSI. Now those are kind of important because in HVAC engineering and equipment, most things are in head of feet, not PSI, except for pumps and whatever, but even pumps are head. So we got to work our way between those two. And so that's formula to use all the time. So if a pump has a leaving PSI of 24 PSI, what is the leaving head? So it's H, it's P times 2.31, which equals 24 PSI times 2.31. Which is whatever it is. I didn't put the answer down. I don't know what it is. Okay, well, multiply those out and you'll get the answer. It's pretty simple. It's somewhere around 50, right? 2 times. So it's 50 something or the other. Sorry about that. That happened. So the second one, a pump has a leaving head of 65 feet. What is a PSI? So if you just divide by 2.31, so it's 65 divided by 2.31, which is 28.14 PSI. That one I actually did. Sorry about that. There it is. It's 55.44. Just in the wrong order. Oh, well. Okay, so that's how you do head. Now, converting water head. So convert a 22-foot chiller barrel, drop into PSI. So this chiller barrel normally come in foot of head. And our balance guys are using instrumentation for PSI. They can measure it in feet of head, but they don't normally do that unless it's a really small pressure drop, like 6 inches or something like that. Then they will use a different scaled meter. But for normal things, so if we have a 22-foot barrel drop, what we want to do is take this formula, which is H divided by 2.31 to get the pressure, which is 22 divided by 2.31, which is 9.52 PSI. So that's how you would do that. Pretty easy formulas. So what will be the pressure be in a pipe from the weight of the water that runs from the first floor to the roof with a total height of 240 feet? Now this is a very, very important calculation. What happens if you don't have enough pressure to keep the pipe 100% full of water clear to the very top? That system will eventually entrain air and could become vapor lock, but if nothing else, it'll have erratic performance. You'll never know why it's working the way it is. So it's very, very important. So here's the deal. So that's, again, P equals H over 231. So if it's 240 feet, it means that water system in that, say it's a chill water system, at the pump, suction, it needs to have 103 PSI. Now that's up 240 feet is getting near the limit of the height of a single pump. Otherwise you need to go to multiple stage, or you need to go to various pumping stations up through the height of the building. And the reason is because that's 103 PSI, and that needs to be set at the suction of the pump. So if the pump is pumping 30 PSI for pipe loss, now you have 136 PSI. Well, That's somewhat of a problem because normal pipe schedule is 125 psi. You can't use that. You'd have to go up to a 340 or something, much heavier weight pipe, maybe 180 psi pipe, but you'd have to go up. So you have to be really careful with this. And I've seen a lot of buildings where they can't figure out what's going on. The temperature is bad in their buildings, and it's all because they don't have the right pressure on the lead of the pump. So anyway, that's a really important calculation. Example, a 22-foot chiller barrel drop that is using 60% glycol, which has a specific gravity 1.1. What is the PSI of that system? So now we have to add back in the specific gravity component, which is H over 2.31 divided by specific gravity. So that equals that H divided by 2.31 by 1.1. And of course that equals this 11 H is 2.1. So we'll get there in a minute. We'll put numbers. So there's the 22. So 22 divided by 2.1. So instead of 2.31 is now only 2.1 because of the specific gravity of the fluid. And that equals 10.47 psi. So that's the psi of this barrel drop with 22-foot of head. Now, what was it with just 22-foot of head? It was 9.52 psi. So you can tell that it's higher because the glycol is heavier than water, so the specific gravity's gone up. Okay, water heat load. So here's the equation to tell how much heat is in water. It's 8.01 times density times C, which is, get it for example, times F is a flow times a delta T. And C, I believe, is a specific heat, but we'll look here in a second. The heat load for a heat exchanger is 100 GPM with an entering temperature of 58 degrees and a leaving temperature of 120 degrees. So it's a hot water heat exchanger. So that would be Q equals 500. Okay, so this right here is a formula to get this in. Here's the 500, and this formula works at water at 70 degrees, plus or minus 10 or 15. So I mean it can be used for. This is a standard formula, and we'll talk about how to offset that. So it's 500 times 100 GPM times the delta T, which is 120 minus 58, and that all equals. When you do that, it equals 3,100,000 BTU. That's what the heat exchanger is capable of doing with these conditions. So what is the same heat exchanger above using a 60% glycol mixture with a specific gravity 1.07 and a specific heat of 0.8093? So the 500 factor, here it is 1 divided by the specific gravity, which is 7.49 weight, at times 60. I'm not sure what the M is for. Times D density times C times 62.45 pounds, which equals 500. So in this occasion, it's this formula, 60 times 1.07, which is the density, specific gravity, times 0.8093, which is a specific heat. So C stands for specific heat. Boy, I don't know why they use those kind of letters for that, but C is specific heat. SH would have been better for me. I don't know exactly what it was offhand. So that's the formula for this. So if we calculate that all out, we end up with 436.09 is now the new factor. So instead of 500, that's the factor. So then if we go back to this other formula, it's now 436.09 times flow times delta T. So instead of using the 500 just at 70 degrees at specific gravity 1, now we have a slightly different factor. So now if we do the same heat exchanger as above, it's the same except the factor has changed. Now our BTU is 2,703,758. So the glycol protects the fluid from freezing, but it doesn't transfer energy as well as water. So the total BTU capacity goes down to the heat exchanger. And this is why I'm always checking this when I check a submittal, because if it has high glycol and you have to have a bigger heat exchanger to transfer the same amount of heat as you would as pure water. So this is the other factor here. All right, flow CV, flow coefficient. Now CV is used in sizing control and balance valves, but can be used to find the flow versus pressure drop of any system. So this is basically a number, and it's a unitless number. It doesn't have any units. It's just a CV, and it's defined as what the system will do at 1 psi pressure drop. So if you have a valve and the CV, that's telling you how much GPM it will flow at 1 psi pressure drop. And we use that to establish a criteria for the valve. So when you do it at different flows, you use that, and you can tell what the pressure drop will be at different flows. And it's a way to collect it. So here's the formula. CV equals GPM times the square root of specific gravity divided by the delta P pressure. And the CV is unitless. Specific gravity is 1 for water. GPM is gallons per minute. F is fluid density at pounds per cubic feet, square cubic feet. And then fluid specific heat is BTU per pounds. And F is fluid GPM, and the delta pressure is in PSI. So not feet, it's in PSI. So if you have a system that's got feet, you got to convert that to PSI before you use this formula. Okay, so now let's, that's the different formula. So if you want to do if you need the delta P, then that's the formula. It's GPM over CV squared. That's the pressure. And the GPM equals the square root of delta P times CV squared. Now all of these, of course, are for water. If you got glycol, then you got to add the specific gravity in there. So here's the formula example. What would be required CV for a chill water valve on a coil that has 50 GPM and with a pressure drop of 5 PSI? Okay, now we're going to talk about some basic engineering stuff that the control valves. A lot of people size control valves absolutely incorrectly. And I talked to them blue in the face. Some of them just don't get it. But the pressure drop, here's where we get into trouble. The pressure drop, this 5 PSI drop, a lot of engineers and designers have a standard spec item that says all coils, all control valves will be sized at 5 PSI. Well, that's an incorrect statement, because the valve should be sized to be equal or slightly greater than the pressure drop of the load is controlling. And that's to get the correct authority over the load. When you have a pressure drop of a valve and your load is half of that, it's okay. It's just that it means you're burning more pressure than you need. But if it's the other way, if the valve has half the pressure drop of the load, now it doesn't control well at all. It will hunt because it doesn't have enough authority over the load. And what that means is, say a valve has 1,000 positions. A DDC controller basically may have 1,000 steps in its software. It says modulating, but electronics doesn't modulate, so basically just steps. So if it has 1,000 steps, but if the valve doesn't have authority, maybe that goes to 600 steps. So all of a sudden you have less control, and then pretty soon it can get really bad because it's not linear. So the valve may not see its control until the valve gets 50% closed. So now you've only got 50% of the throttling range you had before. So this is really important. It shouldn't be just a set PSI. It should be follow the load. And that's how it should be. But, changing minds is hard to do sometimes. So there's our formula. We put these numbers in there. We get CV of 50 times 1 over 5 PSI, square root of 1 over 5. That equals 22.3. Now, valves don't come in point CVs, so that, valves may come, and I don't have this in my memory, but valves might be a 21 CV and a 30 CV and a 45 CV for different sizes of the same valve. So what you do is you select the CV that's the closest. And that's another thing I have a hard time with, is convincing engineers that bigger is not better, especially not in control valves. If you needed 22.3 and you had a valve that had a CV of 21 and a CV of 30, you should pick the 21, because it will control much, much better than a valve of 30. So we need to be careful. Now, of course, you don't want a real small one. If you had 22.3 and the nearest one is 18 and 24, you'd select the 24. You know what I mean? It's in between. But that's kind of a design consideration. So let's do another one. What be the actual pressure drop for a valve with a CV of 24 that is flowing 45 GPM? So then we're going to use the other one, which is GPM, delta P equals GPM over CV squared. That'd be 45 over 24 squared, which would be 3.52 PSI. So now we get the drop. So if you did that and this coil had a drop of 10 PSI, this would not be a good valve. This valve would be a big problem. So the reason this is all kind of important is the control valve is absolutely the most important part. But also when you missize a control valve, and if the designer missized it, didn't realize it, and used that pressure drop for his pressure calculation may be off, because you realize that we need to do control valves with CV, but we also need to size balance valves with CV, because a control valve is controlling the flow and a balance valve is controlling the flow. They're both control devices, so the balance valve needs to be selected. And why that is I've had jobs where the engineer specified that we can't use any valve under 3/4 inch. And then when you went to the flow of the reheat coils, we're way under that. So to balance the job, you had to be almost at close, 100% close. So that doesn't work. The balance valve should have a reduced port in it so that it has some range of controllability to actually provide balance to the system. Example 3, what would be the actual flow of a valve with a CV of 24 and a pressure drop of 6 PSI? What would be the actual flow? So now we're using the other equation, which is GPM square root of delta P times CV squared, which equals GPM of 6 times 24 squared, which would be 58.79 GPM, so you know how much it's flow. So this CV formula is a very helpful formula figuring out what you're doing with a system. You already know what some of the measurements are of the systems. So another example, what would the CV for a chiller barrel that is flowing 150 GPM with a pressure drop of 22 feet, and using that value, what would the pressure drop be if the flow is increased to 160 GPM? Okay, this is where it comes in. CV can be used for lots of other things besides a control valve. So what happens is if an engineered system had a chiller at 150 GPM with a 22-foot drop, but the flow needs to be different in the field for whatever reason, now that drop is not correct. So now you have a challenge if you're a tab guy of, well, where do I set? You know, I set flow by measuring the drop of the chiller barrel. So how do I know that? Well, this will do it. So what you do is you get this formula, it's a CV GPM 1 over delta P, and that would be 1 over the 22 feet and divided by 2.31, which is, we're going to make it PSI. That's making it PSI, right? So that's 48.6. So the CV of this system is 48.6. So now if we want to change the flow from 150 to 160, we would use this equation, which is GPM over CV, and it becomes 160 over 48.6, which is a CV, and then we get a 10.8 times 2.31, so it's 25 feet. So or 10.83 psi. So basically it goes up a little bit because we have more flow. So now that you could balance it to that flow and know you got 160 GPM through it, or if you're trying to figure out what the flow is, you could do that. So this formula comes in really handy for that. What would the CV be for a balanced valve flowing 22.4 GPM with a pressure drop of 1.2 psi using 60% glycol mixture with a specific gravity of 1.1? So there's our GPM times, CV is GPM times specific gravity divided delta P. And this would be a 2.4 over 1.1 over 1.2, which would equal 2.29. So what would the CV of balance would be? A 2.29, because it's a reheat coil, right? Small flow. So the CVs would be small. So now down at the small valves, the CVs do get to be fractional, but big valves, they do not. Okay, pump affinity laws. Okay, so just like we have air fan laws, we have water loss called affinity loss. And this says that the volume Q equals speed times D is the impeller diameter here, not density, it's impeller diameter. So Q is volume in GPM, impeller velocity is RPM, N. So this is RPM, this is GPM, this is RPM. D is the impeller diameter, how big the impeller is. And then DP is head or pressure, and P is power. There's other formulas that have those in there. So head pressure uses DP, which is the head pressure, times speed, times the diameter of the impeller. And then the last one is power. So power, which is kW or horsepower, could be the one. And that's speed times the dimension of the impeller again. So these are water head calculations for us. So see what those, a change in impeller would be. So whenever they make a pump, of course, they make a pump volute designed for a maximum size impeller. And that's what the pump, but then to fit that pump to the design flow, they will trim that impeller back at the factory. And you might get a, you know, if the pump was designed for 12-inch impeller, you might get a 10-inch impeller or a 9.5 impeller. And it's always marked on the pump, the actual impeller diameter, because it's not, these are custom fit to the pump design. So those are the formulas for that. We've talked about that. Okay, example, for a pump that flows 150 GPM at 1150 RPM, what would this flow be at 1750 RPM? So we can do this real easily. So it's Q equals pump times speed. So we have Q1 over Q2 and speed 1 over speed 2. These are really small for me, but it's 150 over Q2 equals 1150 over 750. And we just cross multiply again. And that's Q 1150 equals 150 times 1750, which is 228.26 GPM. If a pump that flows 150 GPM at 1150 RPM and a pressure of 24 PSI, what would its pressure be at 1750 RPM? So using that other one, which is dP times N speed 1, equals 24 over dP over 1150 over 1750 squared again. And that equals this, and cross multiplying again. You get 55.57 PSI. So these formulas allow you to move around within a pump and figure out what it would do at different RPMs and different stages. Change in impeller diameter. So now we have those same formulas. These formulas here for Q for a diameter change, and you get, and remember this, so for this dP is the head or pressure, and it's now a squared. And if you go to power, it's now cubed. So same formula, but cubed. So example, a pump flows 190 GPM at 24 PSI with a 9-inch impeller, needs to flow 150 GPM. What size impeller is needed? Yeah, there's the formula. So it's it's Q1 over Q2 over 9, which was 9-inch impeller over what the impeller we want to find. So then the cross multiplying is D2 times 198 equals 150 times 9, which equals 7.11. So you notice that the impeller's been trimmed because of the lower flow. Now, that's another subject about a pump is nowadays with the prevalence of VFDs, a lot of people just say it's no problem, we'll just use a VFD and slow it down. And that'll also reduce the head pressure, there's no doubt about that. But the problem is, if that pump goes into bypass, it's not going to be running at that speed, it's going to be running at full speed. And now you'll have another, and that doesn't cause a problem if it doesn't hurt the pump. But if the pump is size such that full flow puts it over amps, now you have a problem. So the best practice is always to do the right thing. That's to balance the pump and then figure out what impeller it really needs to have and then trim that impeller. That way the VFD can do its job correctly. Its throttling range, control throttling range will be correct, And if you take it to a bypass, go to full flow, it'll be fine. But not many people do that anymore. We used to do a lot of trimming impellers, but nowadays not so much. Example, what will be the new pressure drop of a pump above once the impeller has been trimmed? Okay, that's a good question. So now we got the formula for squared for the pressure. So then we have a 24, up here it was 24 psi over dP2 equals 9 over 7.1, which we found before, squared. So then we have this as 24 over dP2 over 9 squared and 7.11 squared. And when you cross multiply that, cross that one times that one, you get 14.98 psi. So you can tell that the psi originally was, we didn't say, did we? But that will be the psi at that flow. Well, it's 24 psi. Now we're down to 14.98 because we trimmed the impeller. The impeller is much smaller. Water horsepower. So here's the formula for horsepower equals flow times H times specific gravity divided by 3960. So a pump that flows 2,000 GPM at 64 foot of clean 80-degree water will use what horsepower if the pump is 89% efficient? So it's F times H over 3960 times the efficiency. So it's 2,000 GPM times 64 feet of head times 3960 times 0.89. That's its efficiency. And that equals 36.32 brake horsepower for the pump. This is water horsepower, and this is the brake horsepower of the pump. And the reason is because it's got the motor efficiency in there. So that happened there. So for a pump above, what horsepower would be required if using 50% glycol with a specific gravity 1.077? So now we have to use slightly different. We use a specific gravity, which equals, the pump horsepower now equals 2,000 times 64 times 1.077. That got the specific gravity in there, times 3960 times 0.89. So what we've done is we've just taken the specific gravity and added it together because it's the same except it has pump efficiency. So that's the difference. So now we add that formula, come to 39.11 horsepower, and you see the horsepower went up because glycol's heavier, has a greater specific gravity, so it takes more pump horsepower to pump glycol than just clean water. Okay, shut-off head. Okay, now this is something most people won't ever do, but the balance contractor, this is the way they find out what the impeller really is. No matter what's stamped on the pump, they do this test to make sure it has the correct impeller. Many times the impeller will be specified as at 9.4, and some reason the factory didn't trim it, it comes out a 10-inch impeller. So to find that out, you have to do this calculation, which is head, which is shut off, HS, equals D times N squared, where D is the impeller diameter, and N is the impeller velocity over 1840. And a pump that flows 2,000 GPM with a 12-inch impeller at 1750 RPM, what will be the shutoff head? So if we do that formula, and it'll come out to 12 times 1750 all over 1840 squared, which equals 11.43 squared, which equals 130.26 feet. So it's a pretty high head pump. Pipe pressure loss calculations. Okay, this is, as in ductwork, finding the actual pressure of fittings is somewhat laborious, and so is figuring out pipes. So once an engineer finishes designing a system, laid out all these pipe, has all these coils selected, has all these control valves selected, all these balance valves, and knows the pressure drop of everything, he needs to calculate the total pressure drop of the system. And this is always kind of troublesome. Nowadays, of course, they do it with a computer program, but if you miss this, if you make a mistake on this, it's really a problem. You have a big problem. If you're too low, the only way you can change it by changing the pump. So it's expensive if you mess this up. If you're too big, no big deal. You can trim the impeller and go down, but you can't go up. You can only go down. So this is the process. So from a pipe flow pressure drop, you look this up. You select the PSI pressure drop of the flow and pipe size for the straight pipe, and then you select the equivalent length of straight pipe for the fittings you use. So in other words, you find a table. We have Carrier has tables, ASHRAE has tables. I always like to use the Carrier book for this, but many of them have tables. I also use Crane Flow Fluids for this. And what they'll have, so like here it says this is 2-inch pipe, and this is the GPM. So if you have a 2-inch pipe flowing 20 GPM, the pressure drop per 100 feet is 0.375. So that's what you look up. Now the fittings, this is a fitting table. You also need a fitting table. There's all kinds of those. You need to get those, and Carrier has those in their Carrier manuals. But basically, this is 2-inch pipe and 4-inch pipe, and this is an elbow. And you can see at 2-inch, this is equivalent length, so 5.0, and this is 10 feet. So if you have a 4-inch elbow, it's equivalent to 10 feet of pipe. So all these fittings are listed as equivalent foot of pipe. So let's do an example. A pipe system has 1,150 feet of 2-inch pipe flowing 20 GPM with 10 elbows, 2 reducers, 2 gate valves, and 1 swing check valve. What will be the pressure loss of the pipe system? So I built this little table down here, and this little table has all the quantity of fittings and equivalent lengths, and it comes up with a total of 84 feet of equivalent length. So it's just easy. You take this formula, which is the total pressure drop times the pressure drop of the straight pipe, times the loss per 100 feet, times the pressure drop of the fittings, times pressure drop of 100 feet, all over 100. And so this would be 0.375. That's the pressure loss of the pipe at 20 GPM, times 1150 pipe plus 0.375 times 84 feet, all divided by 100. And that comes out with 4.627 PSI. Now the things that there would have been a lot more stuff in here. There would have been there would have been strainer in here, probably maybe 2 strainers, and then we didn't have control valves. There's a lot of things we didn't have pressure drop in here. But that's how you figure it. Now again, if I was a smart engineer, I'd add 20% to this just to be safe, to make sure I had enough head to do the job. So this is laborious to do manually. The computer programs they have nowadays do it automatically, which is much easier. You have to just make sure you have enough the right input to get the right output. So that's how head pressure is done in the system for water systems. And that's about it for water calculations. That was pretty easy, pretty painless. So hope you have a good day, and please don't forget to subscribe and like. I really appreciate it. And have a great day, and I'll see you on the next one.